If you're enjoying Why This Universe, there's another University of Chicago podcast network show that you should check out, and it's called Capital Isn't. Capital Isn't uses the latest economic thinking to zero in on the ways that capitalism is, and more often isn't, working today. Join Vanity Fair contributing editor Bethany McLean and distinguished professor of economics Luigi Zingales as they explain how capitalism can go wrong, and what we can do about it. Listen to Capital Isn't, part of the University of Chicago podcast network.
So Shalma, since you've been studying physics, what has been the single most exciting physics moment you've encountered so far?
I feel like the most exciting thing I've ever encountered has probably been like gravitational wave measurements. That was huge.
LIGO detecting all these mergers of black holes, right?
Right. I feel like that was the one that I was conscious for. There was also like the Higgs getting discovered, but like I was like 13 or 12 or so. I don't know. I like didn't really know what that meant.
Yeah, I stayed up until the wee hours of the morning to watch that seminar on the internet. Yeah.
Yeah, but it's definitely not that often that there's like totally groundbreaking discovery happening.
When I look back at all of my moments as a physicist, a lot of the most, memorable or exciting ones were these sorts of announcements where, maybe you're even there in person, where you're in this auditorium, like watching the latest, experimental result be announced to the world, and you get to watch not only the result, but all your colleagues' eyes light up as they like lean forward on the edge of their seats. I just love that sort of vibe, that sort of experience. Yeah. When I was first working at Fermilab in the Tevatron era, it felt like these things happened all the time there. There was always, every few weeks, there'd be some new Tevatron measurement, and we'd all show up to see what they had to say. And almost always they were just confirming the standard model. They were, yet another prediction the standard model would turn out to be correct. But, still, like, we learned something in those moments that no human being had ever known before. So on April 7th, 2021, in case you're listening to this podcast, years from now, there's scheduled to be another announcement of this kind. So there's this experiment at Fermilab called the Muon G-2 experiment. And it's a collaboration of like 200 or so scientists from around the world. And they're trying to measure something called the magnetic moment of a particle called the muon. And of all of the physics announcements that have taken place in the last few years, none have I been as excited to hear about as this one. I'm like just stoked with anticipation. I think there's a real chance, I don't know what the chance is, but there's a non-negligible chance that this might be a key moment stepping towards the discovery of new laws of physics.
So as you can tell, we are actually recording the beginning of this episode before April 7th, before the Muon G-2 experiment announces their result. And I hope you can tell we are really excited to hear what this result will be. And so the first part of this episode will be us ahead of the result, talking through, why this is such a highly anticipated result, what it could mean for the future of physics, depending on which way it goes. And then, of course, by the end of the episode, you'll hear our reactions to the actual result that you've probably already heard about. So let's get started with today's exciting episode. You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. My name is Shalma, and I'm a PhD student at NYU.
And I'm Dan Hooper. I'm a theoretical astrophysicist at Fermilab and at the University of Chicago. All right, so let me explain what this muon is and why we're interested in this quantity it has called the magnetic moment. So a muon is a particle a lot like an electron. In fact, it's almost identical to an electron in almost every regard, except it's roughly 200 times heavier or more massive, and it's unstable. So if you just sit an electron by itself somewhere, it will sit around forever. A muon will disappear in about a millionth of a second or so, being replaced by an electron and a couple of particles called neutrinos. So these are really unstable and hard to work with, and they're much heavier than an ordinary electron. So when you take a particle like an electron or a muon and you put it in a magnetic field, it will spin like a top. And every particle has its own response to a magnetic field. They spin at different rates depending on the magnetic field. And the number that quantifies how fast a particle like a muon will spin in that magnetic field is called its magnetic moment. So a lot of things you're familiar with have a magnetic moment. It's not a very exotic quantity or quality. If you take any loop of electric current and put that loop in a magnetic field, that thing will start to spin. That's because it has a magnetic moment. And even the Earth itself has a magnetic moment. So for an individual elementary particle like an electron or a muon or something, the magnetic moment of that particle has to do with how that particle interacts with photons. After all a magnetic field is deep down is a bunch of photons. And in the context of the standard model of particle physics, we know how to calculate very, very precisely what the magnetic moment should be for any given particle.
So to make sense of this, you have to remember that according to the standard model of particle physics, all the electromagnetic force is an exchange of photons, or particles of light, between different charged particles. So the way a particle behaves in a magnetic field has everything to do with how it interacts with photons.
So in this case, the kind of interaction we're interested in is a particle, a muon coming in, and a photon going into that muon, and then a muon going out. So you can kind of picture this. It looks like a tree. The photon makes up the trunk of the tree and then two branches of the muon going in and out. And for that reason, we call this kind of diagram a tree-level diagram, or to be more concrete, a tree-level Feynman diagram, named for the physicist Richard Feynman.
So if you're not familiar with Feynman diagrams, the lowdown is that they are this brilliant way to talk about complicated interactions between particles. And we can even write down the equations describing those interactions just by drawing this little diagram. So even though they look simple, every feature in a Feynman diagram has a technical counterpart in an equation. So tree-level diagrams refer to the simplest version of these Feynman diagrams, basically what the interaction would look like with its simplest possible description in physics.
So if you use that diagram to calculate the muon's magnetic moment, you'll get what we call the classical contribution. So this is what you would have gotten without knowing anything about quantum physics. If you use the old classical equations for electricity and magnetism, that diagram will tell you what you should expect the muon's magnetic moment to be. But it turns out that you need to get this right, to get this precisely right, you need to include all the complicated quantum effects. And these involve what we call loop diagrams. So whereas that tree-level diagram just had, one particle going in, the photon coming in, and then the particle going out, here the particles go in, and then there's some sort of loop of particles before the muon goes out again. So this represents the laws of quantum physics, which say that spontaneously in our universe, virtual particles can come into existence for a brief period of time and then disappear. And if you want to precisely know how a muon will interact with things like a magnetic field, you need to take into account all these possible quantum loops and all these virtual particles that can play a role in these sorts of interactions.
So by drawing extra loops in your Feynman diagram, you're adding the details of quantum mechanics to your equations. For example, the fact that quantum mechanics says that particles can just pop in and out of existence at any given moment. And so that changes what you get as your answer to questions like, what is the magnetic moment of the muon?
So as a couple of examples, just in the context of the standard model, one quantum process that can impact the magnetic moment of the muon is when a muon spontaneously transforms into a particle called a neutrino and a second particle called a W boson. That W boson can then interact with the photon before the W and the neutrino combine again to make a muon. So it's kind of complicated, but that's a loop involving a W and a neutrino that kind of gently changes the magnetic moment of the muon. And you can do this with other things too. There's a similar diagram where the muon radiates or gives off a particle called the Z boson. The muon then interacts with the photon before it reabsorbs that Z boson. These are all the sorts of possibilities that a careful calculation has to take into account. And it's not an easy calculation, but it's the sort of thing that can be done. And there are a lot of physicists who are really good at making these sorts of technical calculations. Okay, so now for a little bit of nomenclature. A particle's magnetic moment is usually written in terms of this quantity called its G factor. And for a particle like an electron or a muon, the G factor at the tree level or the classical contribution is exactly 2. So when we talk about G minus 2, what we mean is the departure from that classical prediction. So that's why we call this experiment the Muon G minus 2 experiment. Take the electron for an example. If you include the one loop diagram, so the simplest quantum contributions, G minus 2 turns out to be about 0.0023228. Okay, so this is like a 0.1% correction to the classical contribution. And this was calculated a long time ago in 1948 by the physicist Julian Schwinger. In fact, for some reason, this was engraved on his tombstone, which I think is a little weird, but, to each their own. More modern calculations of the electron's magnetic moment have been done at hyper high precision, like to 5 different loop levels. So like each one of these loops is kind of radically more difficult to calculate than the one before it, but they've gotten to these like truly heroic levels of precision. And they get a number of G minus 2 for the electron of 0.002319300436. And it's actually been measured to the amount of precision I just said, to 1 part in 10 billion. And it agrees with that calculation precisely. I want to emphasize this is not only the most accurately verified prediction of any theory in physics, but of any theory of anything. Human beings have never made a prediction this precisely in any field of endeavor, intellectual endeavor, as this. This is the pinnacle of precision science or precision whatever thinking.
So in the case of the electron, the Standard Model provides an absurdly accurate prediction of its magnetic moment. But of course, we're not here to talk about the electron. We're here to talk about the muon. And despite these being such similar particles, the story ends up being a little different for the muon.
To calculate the magnetic moment of the muon, it's a similar calculation to the one you did for the electron. And after all, the electron and muon are like really similar kinds of particles. But as it turns out, the fact that the muon is so much heavier makes these sorts of calculations just way more technically difficult. For this reason, it turns out that you can't get this 1 part in 10 billion precision. The best calculations we have to date are like down to the 1 part in 10 to the 7. So it's still very precise, but not quite as precise as we have the electron's magnetic moment nailed down. So physicists have been trying to measure the magnetic moment of the muon for a very long time. These experiments started in 1959 at CERN in the laboratory in Europe. Leon Lederman and others started that program. And those experiments reached a pretty decent level of precision, about 0.4% precision in the early 60s. And by the end of the 70s, they had a precision down to 0.0007%. And all of this agreed with the theoretical predictions. So far, the Standard Model had been very successful. And then in the early 2000s, an experiment called the E821 experiment at the Brookhaven National Lab on Long Island studied how these muons responded to a magnetic field. And they had by far the highest precision measurement of the magnetic moment to date at a level of about 0.7 parts per million. So very, very precise. And the thing that was really exciting about this at the time is the number they measured was different than the Standard Model prediction, bigger by a few parts per million. So if we compare the Brookhaven measurement to the modern theoretical predictions for this quantity, the difference is pretty statistically significant, 3.5 to 4 sigma, which translates to the likelihood of it being a simple statistical fluke being like 0.1% or 1 part in 1,000. So that doesn't seem very likely. So that's kind of where we left off. We have this weird anomaly, this number that we predict one number for, and we measure a different one. And for the last, 2 decades, we've wondered what to think about it. So as I see it, there are 4 logical possibilities. It could be that this is just a statistical fluke. Like I said, this is like a 1 in 1,000 possibility, but weirder things have happened. So we can't rule that out. It seems unlikely, but maybe it's just that. A second possibility is maybe those people at Brookhaven made some sort of mistake in their experiment. You know, these are complicated experiments. It's a really high precision measurement. You wouldn't have to do something terribly wrong to skew your answer at this tiny little level. So maybe that's going on. Who knows? The third possibility is that maybe the theoretical calculations have some sort of error or mistake in them. I would say 20 years ago, that seemed pretty plausible. In fact, back then, there were some errors involving this piece of the calculation called the light by light contribution. But those were corrected, and people have scrutinized this and refined it and worked really hard. And I would say today that seems much less likely possibility than it did back then, but it's still a possibility. And then the fourth possibility, the one that we're talking about the subject for, is that maybe there are other kinds of particles or other kinds of forces that are gently changing the magnetic moment of the muon from its standard model prediction. So by measuring this number, we're actually seeing indications of new laws of physics that we don't currently know about, physics beyond the standard model.
Something you can draw from this is just a measure of how cautious physicists are before getting excited. There's a lot of testing and scrutiny that goes into a result before a physicist will openly call it new physics.
There is a very high standard for something to be called legitimately new physics. And for good reason, though, because anomalies or things we can't explain come and go all the time. Some years ago, there were all these papers about neutrinos traveling faster than light. And it turns out that it was because some cable wasn't plugged in properly in the experiment. And then there was, I don't know how many papers were written about this weird anomaly at the Large Hadron Collider. And it looked really exciting until they had more data in it and the anomaly went away. And, this stuff happens the bulk of the time. But that being said, this looks like a real, contender for being new physics. We don't know, but come April 7th, we'll have a much better idea what we're dealing with here. In particular, the Fermilab G-2 experiment should be able to tell us if this was a statistical fluke. That should be very clear after Fermilab's result. And they should be able to tell us if it was just some sort of experimental mistake. If they get the same sort of number that Brookhaven got, then we can rule out those two possibilities and more or less focus on are we calculating this prediction right? And if we are, then we can focus on the new physics interpretation and try to figure out what kind of new physics might be influencing the magnetic moment of the muon in this way. All right, so let's talk about this actual experiment, the Fermilab Muon G-2 experiment. So, because what we're doing is studying how muons respond to a magnetic field, we have to have a really big magnet. And we're using the same magnet that the Brookhaven experiment used back in the early 2000s. So, and this isn't just some sort of horseshoe magnet, you might have in your desk drawer. This is a 50-foot wide magnet, super, super powerful. And you can imagine this was challenging to move from New York to Illinois. This happened, the move, which we call a big move, happened back in 2013. It was a 3,200-mile trip by a combination of water and road. You can imagine they have to shut down roads when you drive a 50-foot magnet down them in this enormous truck. It was a really big deal. It was all over the news. And they got it and they refurbished it. And it was built into this incredible apparatus. I visited the hall that has the G-2 experiment in it. Now it's gorgeous. And finally, in 2018, they started taking data, and they've been recording data ever since, on and off. And the anticipation is that they should be able to achieve much greater precision than the Brookhaven experiment did with the same magnet, at the level of maybe 5 or 6 times as much precision that the Brookhaven experiment had. And that should really settle the question of whether this was a statistical fluke or some sort of error. It should really clarify the situation dramatically.
So if the Fermilab experiment uses the same exact magnet as Brookhaven did, you may wonder how we can expect to get better results this time.
All right, so around the circular ring, they inject thousands of muons at one time, and they enter the ring with their spin axes pointed in the direction of their motion. So this is like a football being thrown by a right-handed quarterback, just perfectly in the spiral, right? But then the magnetic field, as they go around this ring, causes them to precess or spin like a top. So just very, very slowly, they precess about 30 times for every 29 orbits they make around this ring. So if you measure the rate of that with enough decimal place precision, you can nail what the magnetic moment is and provide a better measurement of this than anyone's ever been able to do. All right, so let's talk about what kinds of new physics could potentially be responsible for the sort of, departure from the standard model prediction that Brookhaven saw, and maybe Fermilab will see in the muon's magnetic moment. So when Brookhaven made their announcement, the by far most popular interpretation at the time was that it had something to do with a theory known as supersymmetry. So supersymmetry is a theory that postulates that there are roughly twice as many particles in existence than are described by the standard model. The ones we haven't seen yet, we haven't seen because they're heavier and hard to produce at particle accelerators. And it turns out that in this class of theories, you solve a bunch of theoretical problems. I won't explain them, but things like the hierarchy problem and things like gauge unification for grand unified theories, all these sorts of technical problems all get solved in the context of supersymmetry. And if some of these supersymmetric particles, in particular the ones we call sleptons and gauginos, yes, I said slepton, that's the real technical word. If those particles are between like 200 and 500 times the mass of a proton, and you pick other sorts of parameters in the theory right, you could generate a magnetic moment for the muon that's about as big as Brookhaven reported back in the early 2000s. There are other theories that have become popular in the same sort of time frame, including ones with extra spatial dimensions, like Randall-Sundrum theories that we've talked about in a different episode of this podcast. And those could do the same sort of thing that supersymmetry is doing here. In the last 10 years or so, supersymmetry has been a big focus of searches at the Large Hadron Collider, and so far they haven't found any of the particles predicted by supersymmetry. It could be that supersymmetry is still real and just right around the corner, but this lack of evidence for supersymmetry has shifted a lot of physicists' attention towards other ideas. In the context of the muon's magnetic moment, in recent years, they've become much more excited about theories in which there exist exotic light particles, particles that are roughly have masses between that of an electron and a proton, so under a giga electron volt of mass. These sorts of particles, if they were really feebly coupled, very, very weakly interacting, and preferentially interact with muons, these could explain the magnetic moment that has been measured without coming into conflict with any other experimental results. So I'd say at this point, all of these ideas are really popular. And then there's kind of one fourth class of ideas. There could be a really heavy exotic form of matter that interacts really strongly with the muon. This would be the hardest one to test of this list of contenders for explanations for G-2. This is probably something we couldn't test at the Large Hadron Collider or any other laboratory experiments we have right now. To test it, we'd probably have to build a collider that actually collided muons together, which is something we've never done. I think we have the technology to do it if we decided to, but it would require a lot of support and funding that at present we don't have.
Right. I mean, like you said in the beginning, muons only last for, this tiny fraction of a second. So to build a collider that can collide, such short-lived particles, that seems really, really hard.
It's not an easy task, but I think if we have any billionaires in the audience there who would like to fund a muon collider, tell them to give me a call. Tell them to give me a call. So if we get the same result that Brookhaven got, maybe with smaller error bars or less uncertainty, we'll know that one of two things has to be true. Either the theorists calculated this wrong, and that doesn't seem super likely, or there's new physics afoot. On the other hand, maybe they'll measure something different from what Brookhaven got. Maybe they'll get a number closer to the standard model value, or maybe right on the standard model value. And we'll know that Brookhaven's result was either just a statistical fluke, or maybe they made some sort of mistake, and the standard model will prevail once again. So one thing I want to kind of take a sidetrack and talk about for a moment is this misconception a lot of people have about what scientists really want. A lot of non-scientists think that what scientists want is for their best theories to be proven correct. They want the data to support their theories. And that's probably true when you have some new theory and you're trying to find out if it's roughly true or whatever. But in the case of the standard model of particle physics, what particle physicists want, they're dying for, is evidence of their theory failing. We're tired of this theory being successful over and over and over again. What we want to do is discover something new. And in order to discover something new, the standard model has to be wrong, or at least incomplete. So, we go to these seminars, we go to these announcements with the hopes that it will be different from what the standard model predicts, because that's the doorway, that's the gateway to discovering new laws of physics, new particles, new forces, whatever, things that aren't contained in the context of the standard model.
Great. So I guess we'll know soon.
We'll know soon. Talk to you on April 7th, Shalma.
So how are you feeling? Yeah.
This is awesome. This is a great day to be a physicist. So just a couple of hours ago, we got saw the seminar virtually on Zoom, and it's confirmed. This anomaly stands. The magnetic moment of the muon is not what the standard model predicts. It's a pretty freaking big deal.
Have you been talking to other people? How's everyone feeling, and what are they saying?
I mean, everyone is a little different how they react to this. Some people are intrinsically calm and mild-mannered, and some people are more like me and excitable by nature. But there's a lot of excitement right now. I mean, right. And there should be. I mean, we don't get this every day in physics. And sure, there's a lot more we still need to learn. They're gonna collect more data. The theory calculations are going to improve. Like we're going to do a lot of things to kind of refine this, but I don't know. This looks like we're seeing indications of real laws of physics we don't currently know about, sticking their nose out.
Right. It's like we've for a long time thought that the standard model wasn't complete. Like we knew that it had shortcomings, but this is the first time that we're really seeing it failing, right?
Yeah, it's certainly the first time like a laboratory experiment doesn't seem to agree. I mean, we know there's dark matter. The standard model doesn't do that.
Right.
It doesn't explain dark energy. It doesn't explain inflation, whatever. But something you can perform in the lab that gets a result that's different from what the standard model predicts. This is the first one.
So are you going to start working on some papers about the muon magnetic moment now?
Well, so I've written some in the past, and I'm certainly going to reread those and kind of refresh myself on some of this stuff. And I'm definitely going to read a bunch of other papers on it. I do have one project related to this, but it's in really early stages. It won't be out for a long time. But I mean, not just me, but the whole community is going to put a lot of thought and emphasis into this in the weeks, months, maybe years ahead.
Right. Yeah, I'm sure everyone's racing to get their idea out now.
So in the, first part of this podcast, we said that there were 4 different logical possibilities for the situation we're in. One of those was that the Brookhaven result was just a statistical fluke, just, a weird 1 in tens of thousands, unlikely, very wrong result. I think we can safely rule that out now. Fermilab's provided an independent measurement of the same thing and got about the same answer. It's not a statistical fluke. The second possibility is that there was just some sort of experimental error done at Brookhaven. Well, we've done it again and got the same result. It doesn't seem to be an error. It'd be a really weird error if we had it twice in 2 completely different experiments. The third possibility is that there's something wrong in the theoretical calculation. I think this is the thing that we have to be the most worried about at this point. I don't think it's particularly likely, but if something's going wrong here, that seems to be the most likely thing. And then, of course, the fourth possibility is that this is a sign, a real indication of particles or forces interacting with the muon in a way that the standard model doesn't know about. Something new, something beyond the standard model, new laws of physics.
Right. I think they said in the thing today, in the announcement, that if the standard model is correct, the odds of this happening would be 1 in 40,000 or something?
Yeah, that's exactly right. So this is a 4.2 standard deviation or 4.2 sigma deviation from the standard model prediction. And the chance probability of getting something like that extremely off is 1 in roughly 40,000. So yeah, this is not a statistical fluke. That this sort of thing doesn't happen from chance alone.
Right. And people have also said that it has to be 5 sigma away to constitute a real discovery, but that's kind of, how do you feel about that?
Well, I mean, so what we call a discovery is entirely a semantic convention, right? We've decided a long time ago that we were going to count something as a discovery if it's 5 sigma, because there are so many uncertainties we generally don't know about or don't think about that can go wrong and can make a 3 sigma result faked more often than you would statistically expect them to be, or a 4 sigma result. So we're being really conservative when we require 5 sigma. I'm fine with us not calling this strictly a discovery yet. But the good thing is this is only the beginning of this experiment. This is the data from what they call run 1. Run 2 and run 3 have already been done, and they're processing that data now. So maybe a year from now, we'll have 5 or 6 sigma if this holds up, and they're doing run 4 right now, and that's in progress. So these error bars or these uncertainties are getting much smaller as they collect more data. So I'm confident we'll get well beyond this 5 sigma benchmark or that landmark in the years ahead.
Right. And I guess to be clear, to explain to anyone who might not be that familiar with statistics, we don't actually need to discover or to keep measuring the G factor to be even further from 2 or something to constitute the 5 sigma. We can just lower our errors, like do a more careful experiment, and that will also bring us closer to 5 sigma.
Yeah, I mean, if you have a evenly weighted coin and you flip it and you count how many times you get tails and count how many times you get heads, the more times you flip it, the more sure you'll be that's a evenly weighted coin. And if it's not evenly weighted, the more times you flip it, the more certain you'll become that it's in fact weighted one way or the other. So yeah, and the same thing is true here. The longer we run this experiment, the more muons are studied and the more times around the circular ring, the smaller these uncertainties get, the better we can measure the magnetic moment of the muon.
Cool. So exciting year to come for particle physics, it seems.
Yeah, for sure. I mean, I expect the preprint server archive is going to just explode with papers on this subject.
Yeah.
A big fraction of all the seminars and everything will be on this subject. And if it weren't COVID times, if you went to a chalkboard in the hallway of some physics department somewhere, you would find G-2 stuff written around on all the chalkboards, and you see people gathered around arguing about the minutia of it. I mean, it's going to dominate conversations and research in theoretical particle physics for, the foreseeable future. It's like Christmas morning.
This episode was produced and edited by me, Shalma Wegsman. Research and writing is done by Dan Hooper and I. Dan is a theoretical physicist at Fermilab and the University of Chicago and is the author of many books, including most recently, At the Edge of Time, Exploring the Mysteries of Our Universe's First Seconds. All music in Why This Universe is produced by Jay Kleinbaum. Thank you so much for your support and for listening, and we hope you tune in next time to Why This Universe.